Next we got rod ratio. So 1.75 is considered ideal regardless of the application. A low ratio equals a high rod angle equals potential for accelerated wear to cylinder walls, piston skirts, and the rings. So a high ratio equals less friction and the air doesn't fill the intake ports with the same velocity, which equals less demand for port flow. Stagnant airflow at low revs and weak torque. So low ratio is more wear, vibration, and heat, shorter engine block deck height, more vacuum at a lower RPM, better throttle response, more low end torque. Common daily drivers and street performance vehicles would have like a low ratio. And high ratio would be less friction, wear, and heat, holds compression and improves combustion efficiency, less vacuum at low RPM, poor throttle response, less low end torque, and it's common in race engines. So 1.4 to 1.8 is equivalent to street engines and normal road cars. Angulation between connecting rod and crankshaft is reduced when the longer rods push the piston higher. So when the rod to stroke angle increases, the angulation decreases. The piston stays at the top dead center for longer, which equals dwell. Longer rod equals piston acceleration is slower, moving away from top dead center, which equals longer dwell. This equates to maximum torque and maximum engine power. So like further aids in cylinder filling, especially at high RPM, equals engine rev limits increase. So then it hurts low RPM torque because air velocity in the engine is actually reduced. This can be noticed by lower engine vacuum, which equals less airflow. Expect worse mixture of air fuel because of that, less airflow. Rev range is the answer here, and long rod ratio is better suited for a higher RPM. So I believe this demonstrates that the design of these engines are in the higher RPM range, and that's for work. It also supports the fact that they are reliable, high mileage engines because of less wear and heat. Some say that higher rod ratio in the 318 has pistons stopped longer at top dead center, which gives complete burn of the fuel and moves away slower, which equals more time for pressure on the piston, equaling more torque. This is where people say heads are where all the power comes from, and upgraded the heads are a must. But you should also have a bigger cam to take advantage of more flow with upgraded heads. Here's an example of the rod ratio here. So what you're going to do is you're going to get your rod length, which is consistent with all three Dodge small block engines with 6.123 inches, and that's from the center of the small end to the large end bore there. That's where they're getting that measurement. So you take your rod length and you're going to divide it by your stroke. So over here we have an example here. So the 273, 318, and 340 all share the same stroke. The 360 is 3.58, and now you can get stroker kits to change that. And these are the two that I found for the research I was doing. So you take those numbers and you're going to plug them into the equation, and then this is where you're going to get your rod ratio, and this is what's showing you, the highest is the 318 with the largest number, and then we're going down to the lowest, which is actually with the 4-inch stroke. So this is where you can see that stroker kit is going to reduce that rod ratio, and that's what you're going to want to get to improve your torque. And as we look at this is the example here when we're saying that like the 318 is known for its dependability. And with that longer rod ratio at 1.85 to 1, that's where, the high ratio is less friction, wear, and heat. right? And so that's what's making for the engine durability and lasting longer, right? So in my opinion, I think that's kind of the secret. Also, too, notice that the 340 has that same rod ratio. So what's the magic with the 340? Well, what they did was they maintained the same stroke with the 340 at 3.31, but then they supersized the piston to 4.040. So basically it's got a 40 thou over on a 360 piston with the same stroke as the 318. So it's kind of like they took the best of both and put them together, and that's, you know, the magic sauce for that 340. Compression height is the distance from the center of the wrist pin to the crown or the top of the piston. Deck clearance is the distance between the top of the piston at top dead center and the surface of the deck or the top of the block. So positive would sit in the bore and a negative would protrude above the block. Positive deck clearance would be if this piston here is down in the bore, because that's going to be added to the combustion chamber in the head. And negative is if this piston is above the top of the block, because that amount of material has to be subtracted from the combustion chamber in the head. And that's why this one would be positive, it's added to that number, and this one is negative because it has to be subtracted from that number. Quench height. The quench height equals the distance between the flat top of the piston and the cylinder head surface at top dead center. This is going to include the gasket, but not combustion chamber in the heads, and the positive or negative deck clearance, so it only goes to the flat surface of the head. That means anything, so we've got a gasket on here. So that means that includes the gasket and anything from the top of the piston to the top of this gasket. Anything above that gasket is not included. And that's what they're talking about when you have your quench. And according to that definition, that means that none of this material in the head is included in there. It stops at the top of the head here. So anything from the gasket down is what they're calling as the quench. None of this would be included. Quench is supposed to create turbulence pushing mixture towards the spark plug. That equals a better burn, reduces detonation and exhaust emissions. Good quench reduces ping because the space is so small. Ideal quench is around 38 thou to 43 thou with steel connecting rods. Note, less than 6,000 RPM equals a max of 32 thou. The ping basically equals air and fuel mixture igniting incorrectly. And the reasons for ping include low-grade gas, carbon buildup, bad spark plugs, timing over advanced, engine too hot, which equals pre-ignition. Quench to me is basically, again, increasing that combustion ratio. The higher the combustion ratio, the smaller the space is, and that's kind of the way I understand it with the quench. It gets a little confusing when you're not adding the combustion chamber in the head, to me personally, but that's the information that I come across. So if I've done this correctly, this is the deck clearance calculation. So I got 1/2 the stroke plus the rod length plus my compression height, which is that 1.810 from the piston. 1.810 from the piston. So we've got our stroke divided by 2 plus our rod length plus that compression height, and this is what we're getting for our answer. So then we take the block height, and this is, if you remember, I was getting some different information back when we started out on what the actual block height was, but this is one of the numbers that came up, and it actually works out with calculation, because when I measured it over there, it ends up being 3 thou, and that's what we ended up getting here. So here's our block height with the 318, and then we're going to input our number there, and we've got a difference of 3 thou. But the compression height number is more, so that means that we've got a negative deck clearance because our piston is actually above the block by 3 thou. That gives us the negative. So we have to subtract that 3 thou from our quench space. So if we have our head here and we have our gasket, and in between the top of the piston to the top of the head is our quench space, we ended up with the gasket thickness. I just measured that used gasket there at 43 thou. Then we've got our negative deck at 3 thou, so we've got a clearance of 40 thou, and that's going to equal our quench according to the definition that we researched. Next, we're going to calculate the compression ratio for this engine. And full disclosure is that I did all this calculating before I went and took it and got all the work done. So some of the numbers that I've used don't match what we ended up with when we came back, but it'll still show you how to do it, and the number that I have won't vary a whole lot from what the actual compression is for this engine. So our compression ratio starts out with this equation. Compression ratio equals displacement volume plus clearance volume divided by the clearance volume. So our displacement volume right here is going to be our bore divided by 2, and then we're going to square that, and then multiplied by pi multiplied by stroke. So we've got, originally we started off with a 3.91 bore, and then we went 30 over, so that's what gives us our 3.940, and then we're going to divide that by 2. We're going to square that, multiply it by pi, multiplied by 3.31, which is our stroke. So we get 40.335 cubic inches. Now, when we're doing our compression ratio, we got to switch that to cubic centimeters so we can get our accurate number. So we have to take that 1 cubic inch equals 16.387 cubic centimeters. So we're going to take our 40.335, we're going to multiply it by our 16.387, and we end up with 660.96 cubic centimeters. So we've just calculated our displacement volume. Now, if we want to know what our the engine size is now after that, that's where we have our 40.335, which is our cubic inches. And we're going to multiply that by 8, and that's going to give us 322.68 cubic inches. So where this was a 318 cubic inch engine, now we have a 322. Or if you want to round it up, a 323. So next is our clearance volume. So we've got to figure that out. So clearance volume equals the piston volume plus the deck volume plus the gasket volume plus the combustion chamber volume. So this is where I was talking earlier. When I did this calculation, according to the pistons that I bought for this project, they were supposed to be 12 thou into the hole. So we'll continue through with the calculations, but in fact what happened was we're 3 thou above. So basically this whole part here will be removed from our actual answer. But we'll go through the exercise anyway. Piston volume equals the cylinder diameter divided by 2 squared and multiplied by the height. So there again we have our bore, which is 3.940 divided by 2 squared, and then we're going to multiply that by what we thought was 12 thou deep in the hole. And this was the answer that we got. So we'd take that answer, and then again, we're gonna multiply that by our cubic centimeter calculation here. So we take that, we multiply it by the cubic centimeters, and we get 0.76 cubic centimeters. Now here's the other thing. You had to add the 5 cc's because the pistons have these little reliefs in here, and right from the factory on the box, they were calculated at 5 cc's. So you have to add that to the number. And when we add that to the number and we finish our calculation, we ended up with 81 cc. Next, we have to calculate what our gasket is. And this is, again, information that I got off of the internet when I was trying to calculate all this out. So according to that information, it ends up being squished down to 28 thou. And the circle of the gasket, so they're saying that this circle here measured out, that is going to be 4.040. So these are the numbers that we need to input into the calculation. So we have our bore, 4.040 divided by 2. We square that, multiply it by our thickness after the squish, and we come out with 0.114. We again take that, we're going to multiply that by our cubic centimeter conversion, and we get 1.87 cubic centimeters. And then after much discussion, it seems to be everybody agrees that the Magnum head combustion chamber volume is 62 cc's. So that's what we're going to use for our calculation here. And then we have our clearance volume. So the clearance volume is equal to the piston volume plus the deck volume, or how much the piston is down in the hole, like how much that space is, plus the gasket volume, plus the combustion chamber volume. So we know that the reliefs in the piston were 5 cc's. So we've got our 5 cc's for that. This was our calculation for if the piston was 12 thou in the hole. It is actually not 12 thou in the hole, so in reality, this wouldn't even be added to the equation. So then we have our gasket, which came up at 1.87 cc's. And basically that could vary. Like, I mean, for the numbers that I just run up here for this gasket, we've got lots of room to make up for this difference. So that's why I say the end result will be pretty much the same. So then we're going to add our combustion chamber from the head, which is 62 cc's, and we get a total of clearance volume of 69.63. And once we take that, we go back to our original equation, which was the compression ratio equals the displacement volume plus, which if you recall was 660.96 cc's, and we just calculated out our clearance volume, so plus the clearance volume divided by the clearance volume. So 660.96 plus 69.63 divided by 69.63 is going to give us 10.49 to 1. So about a 10.5 to 1 compression ratio is what we should expect out of this engine. Hopefully all that makes sense, and that's where we're at right now. We got to finish doing some work on those heads, and once all that work is done, then we can start assembling the rest of the engine here. Interesting, after correcting that calculation, and the correct number is 68.67. So after we finished our calculation, we got 10.625 to 1. So it went from 10.449 to 1 to 10.625 to 1. And that was a difference of 15 thou. The 15 thou was the 12 thou in the hole, which was incorrect. And then we added that negative 3 thou out of the hole. So 12 and 3, we've got 15 thou difference, and that's how much it's changed the compression ratio.